Welcome back, lecture 45. Today we are wrapping up sigma notation. Not that we're going to put it aside and not use it, but we are going to set it aside for today for the most part. We do have one problem to finish with sigma notation. Then we're going to go on kind of back up to the regular part of the book, back up into chapter 5, and look at how antiderivatives are going to be used. Even though today we won't use them, we'll put the concept of area together with the sigma notation, and when we get to section 5.2, we'll actually be using definite integrals to find areas under curves. So we were at the latter stages of a problem. Let's finish that up. Hopefully, if we have time for questions today, we can do web-assigned questions, because I know there are a couple of those that are out there. This was a problem that we started with about 3 or 4 minutes to go yesterday. We combined algebraically some stuff. We distributed the 3 over n to both pieces, keeping in mind that the indexed variable is I. So the things that are I are changing. The things that are not i's are not changing. So we can, in a sense, factor those out in front. So here we've got 3i squared over n cubed. Distributing here 3 over n. The I squared is going to have to stay. In the argument, the 3 over n cubed can come out front. 3 over n can come out front, which leaves 1 in that position. Now this one we did simplify. What is the sum of 1 from I equals 1 to n? What is 1 added to itself n times? That is n. And this n reduce, so we get a nice clean 3 out of the last part of this problem. So here's where we are and what we need to finish up today, if possible. So we do have a 3 in the numerator and a 6 in the denominator. I'm going to kind of put those off to the side together. And then we're going to have an n plus 1, and a 2n plus 1 all over n cubed. And I'll go ahead and put this in. We've simplified the last term, and we now have 3 here. 3 over 6 is 1/2. I'm not going to multiply all this out, but if I were to multiply to create the first term of this cubic polynomial, what would it be? 2n cubed, right? n times 2n would be 2n cubed. Are you convinced that everything else is of lesser degree? Okay, so I'm just going to put some dots here. So everything that follows the 2n cubed has an n squared in it, or an n, or just a constant. Actually, it would stop with just the n's, right? Now, we'd have to have a little more additional information to simplify this, but let me throw this in, and we're going to have this when we get back into the book, into chapter 5. Let's suppose that we wanted to take a limit of this as n approaches infinity. So we want, and I'll show you in just a couple minutes why we want n to get larger and larger and larger, and ultimately to approach infinity. That does not affect 1/2. How does it affect 2n cubed plus some stuff of lesser degree over n cubed as n approaches infinity? Makes it 2, right? Doesn't this thing approach 2 as n approaches infinity?
Why do you have the dot, dot, dot instead of multiplying everything out?
Because it's of lesser degree, so it's got an n squared in it and an n in it. So don't you compare, we've done shortcuts on this limit. Don't you compare if the degrees are the same, numerator and denominator, it would be the quotient of those coefficients.
Yeah.
We've done that in here a couple times. So it's going to be 2 over 1, so it really doesn't matter what follows, it's of lesser degree. So this piece that I circled approaches 2 as n approaches infinity. And then even though we started with a bunch of n's and i's, we end up with a numerical answer.
Cool.
So we've got 4 for the problem that we started with. Of course, we'd have to have a little more information. We'd have to have out in front the limit as n approaches infinity. And let me backtrack, and if you have a question, then we can. This summation, we're starting I at 1, and we're stopping I at n, right? So if we allow n to go to infinity, what are we saying about where we're stopping it? We're not stopping it. We're letting it go all the way to infinity. So it may not seem like something like that would have an answer, like a nice clean answer like 4, which this does. But you'll see a lot of that in the problems that we're going to use our sigma notation and our 3 shortcuts. Our 3 shortcuts are these, and then we'll go back into the chapter 5 where we're going to have to put this stuff to use. 1 added to itself, n times is n. The sum of consecutive integers from I equals 1 to n. What did we decide that was? N times 1 more than n, all over 2. And the sum of consecutive integers squared from I equals 1 to n. That one's kind of an ugly one. N times
2.
n plus 1 times 2n plus 1. That's what we just used in that the rest of that problem that we finished up, all over 6. So we will use all 3 of these as we get back into the kind of the body of the book. They're in chapter 5, but there's not much else. It just says, do you remember how to use this? And I guess hopefully now you can answer yes to that. All right, any questions about the appendix? Appendix F in the back of the book before we move back up to the regular part of the book. Okay, so we did 4.9. That got the thought process of antiderivatives going, reversing the derivative process. And, if we know the derivative, can we find the function for which it is the derivative? That may not seem like this is related at all, but we'll kind of make this tie-in. When we get to 5.2, how does antiderivative and sigma notation, how does that all fit in with area under a curve? Now, in this section, we're going to do approximations of areas. When we get to 5.2, we're going to forego a lot of the arithmetic and the manual labor, and we'll be able to actually use calculus to get area under a curve. So we're going to have a region, just to start with a simple region. It's some function, and we'll make it above the x-axis, and we'll also make it in the first quadrant, just to start with things that are simple. And we want to be able to, using integral calculus, antiderivatives, we want to be able to find the area under this curve. So the approximation technique that we start with is to take that region and subdivide it into rectangles. So let's say we want to subdivide it into 4 rectangles. And those aren't rectangles yet, but we can choose. This doesn't have to happen this way, but I made the widths of each rectangle the same. That doesn't have to be true, but it kind of is a good place to start. So all of these are some delta x wide. And all we need to do now is figure out the height. So again, to try to be uniform in how we approach the problem, one way is to take the left-hand endpoint. So let's take this left-hand endpoint and use that to generate a rectangle so that we can approximate the area under this curve. Now, it is an approximation because you can see the pieces that you're missing here, here, and here. And you can see on this rectangle we've actually got a little overlap. So we don't have enough on the first three, and we've got a little too much on the fourth one. Kind of depends on the shape of the curve, how that goes. So the area, let's call A x sub 0. Let's call this next place that we stop x1. Let's call that x2, x3, and our b value, let's call that x4. So the initial x is just x sub 0. You can number these however you want to. So what's the height, or excuse me, what is the area of the first rectangle? Well, it's the height of the first rectangle. How tall is the first rectangle? It's this tall. What is that? Isn't that the f of x0? Is that true? The first rectangle is the f of x0, tall. How wide is it? Delta x. The next rectangle, here's how tall that is. How tall is that? F of x1. The next rectangle, that distance generates its height, f of x2. And our last rectangle, f of x3. So we've got these four rectangles. We know it's an approximation. How good it is depends on how well the left endpoint, as we draw the height over, as we draw the lid to the region, as we draw it over, how much it actually matches the curve. If the curve goes up rapidly, we're going to have a lot of error. If it's a fairly gentle slope to the curve, we're not going to have as much error. Let's convert that from its expanded form into a sigma notation. Well, what is true in every piece of this expanded sum? There's certainly a delta x in every one. And let's index, let's put something in here that starts at 0 and goes to 3. Now, if it starts at 0 and goes to 3, 0, 1, 2, and 3, that's 4 regions, right? So also in the argument, we want the f of x sub I. X sub 0, x sub 1, x sub 2, and x sub 3, and that's what we have. I starting at 0 and going to 3. So I know that's a little small, and we've got some subscripts here. F of x sub I times delta x. So, what would make this process better? We've got 4 rectangles. We're missing this piece, we're missing a little bit here, and we've got a little extra here. What? More rectangles. If we had more rectangles, we would probably do better. So instead of having 4 rectangles, and we're not going to do this computation, this is where you set it up and allow a machine to do it, or another process that emulates what the machine does. If we had 100,000 rectangles, we'd probably do a pretty darn good job of finding the area under any curve. But it's an approximation. Could we take the same curve and instead of taking the left-hand endpoint, I'm going to leave out the a and the b. I'm going to call this x0 and call the b value x4. So we still want the same area. It's still the same f of x. But instead of choosing the left-hand endpoint, let's choose the right-hand endpoint. So we've got kind of the opposite situation, is we've got too much area in these first three, and we don't have enough in the last one. So how will that look? Let's go directly to, they're all delta x wide. Start at 1. Now the height of the first rectangle is the f of x1. And if we want 4 of them, if we're going to start at 1, we better end at 4. 1 and 2 and 3 and 4. There's our 4 heights. Here's the height of the second rectangle. Here's the height of the third one. And here's the height of the fourth one. So we still want f of x sub I. We're just starting I at 1 instead of 0. Now, what would be really nice is if we could find the area up here by using the left-hand endpoint, or left box, I think it's called in Maple, and the right box, and take the two and average them, right? So if we took our first area and our second area and averaged them, that's probably pretty darn close to the actual area. Again, you're going to do better by having more rectangles. So as we have more rectangles, notice what happens. N, which is kind of the number of entries that we have, it's this upper number up here, this 3 and this 4, our n value gets larger and larger and larger. And what happens to delta x as it gets smaller and smaller to the point where it's practically 0? And when we get to that place where we have an infinite number of rectangles and they're so skinny that each one is practically 0 in width, we're going to get the exact value for the area under the curve. So these are the things that eventually we want to happen. Let's take an example, a couple of different ways, and we'll keep it fairly simple. So we've got the curve y equals x squared, and let's say we want to find the area under this curve from x equals 0 to x equals 1. And the first time through, let's take 2 rectangles. It's going to be very poor. And let's take the right-hand endpoint. So 2 rectangles. We'll use the right-hand endpoint to generate the height of each one. So we've got a total distance of 1, and if there's only 2 rectangles, each one is 1 minus 0 divided by 2. That's how wide each rectangle is going to be. In general, that'll be b minus a divided by n, right? Right endpoint minus left endpoint divided by n, where n is the number of rectangles. But we've got a nice picture, so here's our first rectangle, and here's our second rectangle. So we're not going to do very well this time. In fact, we're going to have way too much, right? We want the area under the curve, and we've got quite a bit of overlap here and quite a bit of overlap here. But let's see what it is. So it's an approximation for the area. Each one is delta x. Well, we know what delta x is. It's 1/2. Each one is 1/2 wide. How tall is the first rectangle? F of 1/2. Well, what is the f of 1/2? Here's the function. 1/4. So 1/2 squared. So I could put in here f of 1/2. I'm just going to go ahead and write down what the f of 1/2 is. And the next rectangle is the f of 1 tall. What is the f of 1?
1.
It's 1. So we've got 1/8 plus 1/2. So what is that? 5/8. Point, what is 5/8? 625. Questions on that? So it's all computation.
I have one. Where did the 1/4 come from?
Where did the
1/4 at the top-ish.
Here.
There, yeah.
That's the f of 1/2. So here's the height of the first rectangle. So we put 1/2 into the function. The function is a squaring function. So 1/2 squared is a 4. This is the f of 1. Put 1 into the function. The f of 1 is 1 squared, which is 1.
Okie dokie.
Way too much. Way too much area. Yes?
In general, will right Riemann sums be a normal over approximation, or just depend on?
Okay, that's a good question. So he's talking about in general, would the right rectangle or the right box, the way we've constructed it here, or this is sometimes called circumscribed rectangles because we're over the area. If you use the right one and it's an increasing curve like this is, it'll always be an overestimate. If you use the right one and it's a decreasing curve, it'll be an underestimate. So it kind of depends on the shape of the curve. All right, any questions further with that one? So with two rectangles, we got the area to be 0.625. We know that's way too much. The level of accuracy is real poor. So let's take the same diagram. Let's see if we can do better. Now we'll stick with the same format where we choose the right-hand endpoint to generate the height of the rectangle. But let's move this time to 4 rectangles. And we'll use the right-hand endpoint. What's the width of each one? Okay, it's easy this time because the total distance is 1 and we have 4 of them. So in general, it's going to be your right endpoint minus your left endpoint, all divided by the number of rectangles that you want to generate. So in this case, it's 1/4. So the area, we're using the right endpoint again. So I'm hoping, and I think we'll find this to be true, is that even though we've got some overlap, it's less severe than it was when we had just 2 rectangles. So what's the area of the first rectangle?
1/16.
1/16 tall. How wide? Well, they're all 1/4 wide. So that's this distance, 1/16. Now we want this distance, which is 1/4 times the width, which is 1/4. Now we want this distance. It looks like it's 1/2. It's actually a little larger than that. It's 3/4 squared, which is 9/16. And the last one is 1 unit tall and 1/4 of a unit wide. So we've got some more arithmetic to do. That always happens when you've got more rectangles. So we've got our area is what? 1/64 plus 1/16 plus 9/64 plus 1/4. So I guess we could change everything to 64ths. That's already 64ths, and so is that. 1/16 is 4, and 1/4 is 16. 64ths. So we've got 1, 5, 14, 30 64ths. What is 30 64ths as a decimal? 46875. Is that what it is exactly? 0.46875. So the first time with two rectangles we got 0.625. Now we're closer to the actual area under the curve, which is 1/3. Okay? Actually significantly closer to the actual area under the curve, 0.46875. Catherine?
Can't you just, I mean, like, I guess it's just, I don't know, I just think it's easier to take out, just add up all the heights and then multiply by
Yes.
1/4.
Right.
Okay.
So you're basically doing what we decided could be done here. They all had a 1/4, right? And then these are the f of x sub I from I equals 1 to 4, right? So she's saying they all have a 4th. Why don't we just factor that out and then add together all the heights? 1/16, 1/4, 9/16, and 1. That'll work. Now, it gets a little redundant, this process, when you go from 2 rectangles to 4 rectangles to 8. I mean, we could do it. I mean, it's not difficult work. It's manual labor is what I would call it. But if we wanted to go to, let's say, n equals 10, okay, let's use this instead. Okay, for n equals 10, now we've got 10 rectangles. How wide is each rectangle? 1/10. If you found these regions, again, we're using the right endpoint, it'd be 0.385. If you go to n equals 30, let's not actually do that. Let's use this picture and assume that we did it. You can see that the error is even less. The actual area is, again, 1/3. For n equals 50, well, you can kind of see how, even from the diagram, that your error is, it has to be less. You just got significantly less overlap here than you have on this picture right here. So with 50, the area is 0.3434. Still more than 1/3, but it's getting pretty darn close to 1/3. Now here's the underestimate. Now we're using the left-hand rectangle, the left-hand endpoint, to generate the height of the rectangle. Not enough. Actually significantly less than the actual value. With 30 rectangles, there's the estimate, still an underestimate. And with 50 rectangles, there's the estimate. Getting closer and closer and closer, coming in from the other side to 1/3. Here we're getting closer and closer to 1/3, but we're still above 1/3. Jonathan?
If we average those numbers, how close? Would it still be pretty inaccurate?
It's actually pretty good. If you would take these two, the ones with 50 rectangles, and if you took 0.3434, just the decimal that appears here, and added it to this, and took half, that's probably very, very close to 1/3.
Is it the same for the ones on the left side?
Yeah. It won't do as good. You'll do better with the average just the same way you did better with each individual value with the more rectangles. Questions on this? This is in your book. Just a diagram that I copied so we'd have less computation to do in class. And you could see how the areas are getting closer and closer to the actual area.
So in order to do that, you would use the sigma notation.
You would need...
You would use the sigma, or the whatever.
You could, to get exact, you would use that other S that we actually haven't come up with, yes, that S that it looks like an elongated S, this one. And you'd do an integral, and then you'd actually do a definite integral. So that's kind of where we're headed. We're not there yet. What would be wrong with, we've got our region here. We decide that the left-hand endpoint and the right-hand endpoint, that's really not getting us there. We don't want to do both so we can average them. How about instead of taking the left-hand endpoint and the right-hand endpoint, how about if we took the one in the middle of each region? That might actually work a little better. So instead of taking x0 or x1, let's go to the middle, come up here to the curve, let that generate the height. What's the advantage?
Much more than
Kind of splitting the difference, right, of the part that's too much and the part that we're missing. So come here into the middle of this one. Come up to the curve, let that x value generate the height. Same thing in this region. And same thing in this region. That'd probably be a good alternative to doing 3 or 4 different things and then averaging them in pairs. So it is possible, and the authors talk about that in section 5.1, of using the midpoint to generate the height. So you still would have to find delta x to find kind of the left endpoint and the right endpoint so you'd know where the middle actually was, and you'd put that into the function. So I think the authors use this. This notation. They'll use a little x with a bar over it, and that is the midpoint of that region. So you'd take x0 and x1, add them together and take half, and then decide what to put in there. Or the next time through, you'd put in x1 plus x2, add them together, and take half. So it's the average of those two values.
Why is there an N on top?
An n, well, in this diagram, we want 4, right? But in general, when we want n rectangles, that can change. So on this picture, n is 4.
Like you're doing
Right.
Why wouldn't you say f of x to the 1/2?
The notation won't handle that because there is no, these are kind of discrete numbers that there is no x sub 1/2. There's an x sub 0 and an x sub 1, and then the next x value that you encounter is x sub 2. So to generate the one in the middle, you really have to add the 2.
Okay.
So it's a notational thing, but that's really what it is. You're picking the value halfway between x0 and x1, halfway between x1 and x2.
Okay.
But this is a integer approach to scrolling through the different regions. All right, let's say we have a velocity in time chart. And we want to use that velocity in time chart to generate distance. So we'll have a chart. From the chart, we'll make a rough table. We don't really have a continuous graph, but we know the graph is continuous. All we have are entries. At time 0, the velocity is 25 feet per second. At time 5, the velocity is 31 feet per second.
Where are you getting this from?
I just have a table of values handed to me.
Okay.
At time 10. So it's data points. So you're analyzing at certain points in time. The 0, where are we starting? This thing that's moving starting at 25 feet per second. 5 seconds later, it's going 31 feet per second. 10 seconds after we started, it's going 35 feet per second, and so on. So those are times, time in seconds, and velocity in feet per second. So if we just have some data, we don't really have the whole curve itself, can we estimate the distance that this thing has traveled during this time element?
Over approximation.
Well, I would settle for either one. Can we, in a sense, make our own curve,
Yeah.
even though we don't have anything else other than these points? We don't even know if we can connect these points to one another, and if they connect, how they connect. We don't know what's going on at time 2 or 3 or 4. We just know what's going on at time 0 and time 5. So the picture for this, where this is time in seconds, and this is velocity in feet per second. At 0, it's at 25. What do we have here? 40, we're going 10, 20, 30, 40, 50. So at 0, we're at 25. 5, 10, 15, 20. At the 5-second mark, we're at 31. At the 10-second mark, we're at 35. 15, we're at 43. 20, we're at 47. 25, we're at 46, just a hair under that one. And 30, we're at 41. 5, 10, 15, 20, 25 to 30, 30, we're at 41. So here's what we don't know. We don't know how to connect these dots. I don't know if I'm going to connect this by something that's concave up or something that's concave down. I don't even know that I can legitimately connect them at all. I mean, I guess I can, right? It was moving at time 1, 2, 3, and 4, time 3.3, time 4.7, but I don't know how to connect them. But can I still approximate the area under this curve even if I don't know the curve?
Yeah.
We can use these data points. So I don't know, we haven't done a left rectangle yet. Let's use the left-hand endpoint to generate the height. Okay, so there's 0, 5, 10, 15. So that'll approximate the area under the curve. And by the way, what will the area under this curve be?
Positive.
It's a velocity curve. What's the area under a velocity curve? It's a distance, right? Let's validate that it's a distance. How tall? Let's take this first rectangle. How tall is that rectangle?
25.
But it's 25 something. 25 what?
25 feet per second.
It's 25 feet per second. And how wide is that first rectangle?
5 seconds.
It's 5 seconds. What do you get when you multiply feet per second by seconds? You get feet. These knock out, right? Seconds in the numerator, seconds in the denominator. So for the area of the first rectangle is what?
25 feet.
125 feet. That's an estimate. That's the best we can do right now. That's an estimate of the distance traveled during the first 5 seconds for this thing, whatever it is, that has only 2 data points for us to deal with. What's the area of the second rectangle? I don't know that we need to find them all, but let's at least find
31 times
Okay.
5 feet.
31 feet per second times
5 seconds.
5 seconds. They're all 5 seconds wide. So before they were just like a quarter of a unit or a half of a unit. Now it's got some units attached to it, seconds. seconds reduce when you multiply 31 times 5 is
155.
155, and it's got a unit, it's feet. So the first area is 125 feet. That's a distance. We would add to that the second area, 155 feet. And we don't even have a curve. We don't have a function. All we have are data points. So whether you have a curve and you kind of generate your data points from the left or right-hand endpoint, or whether you have a data set and you don't even know what the curve looks like from one point to the other, you can still approximate the area under that curve. And it just so happens that the area under a velocity curve is, in fact, distance. It's some velocity tall and it's some time wide. And if those are in agreement, which they need to be to do the area anyway, then your unit time, they're going to knock each other out, and you'll be left with just a unit length, which is distance. Question?
Shouldn't you go ahead and finish working that out? Because when you do left Fremont sum, wouldn't you not use the 30?
Yeah,
When
we
you're
don't.
doing it?
We're not going to use the 30, right? Because the 41, which we go from here to here, that's not going to be the height of anything, right? We're using the left-hand endpoints, and we generated 1, 2, 3, 4, 5, 6 rectangles, and we've got how many data points? 7. So what Kent is saying is true. This is a data point, but we don't use it using the left-hand endpoint to generate the height. So not that it's not important. It is important, and we would use it if we were using the right-hand endpoint. But for this one, we're only using 1, 2, 3, 4, 5, 6. These 6 to generate our 6 rectangles. So our last one, our 6th region, would be 46 feet per second tall times what? 5 seconds. They're all 5 seconds wide. So that's our last one. We don't use the last data point. Thank you for pointing that out. That's probably worth pointing out.
Couldn't we go the other way too and not use the last data point on the left?
Yeah, if you use the right-hand endpoint, then this rectangle would actually be your first one. So this would be your first rectangle, right?
Mm-hmm.
And then this rectangle would actually be your second one.
Right.
And then you'd need to add in the last one, which would have height 41. All right, WebAssign question, if we can get a quick one. That anybody want to ask a WebAssign question?
I'm going to look at it tonight. It's over with. It was due last night.
Still might see it again.
True. Hopefully not.
This is true. Not trying to be mean, just trying to test you on what you've done. Anybody? Anything?
I have a question.
Katie?
A car brakes with a constant deceleration of 40 feet per second squared.
Okay, wait a second. Constant deceleration of
40 feet per second.
what problem number is this?
15. Producing skid marks measuring 160 feet before coming to a stop.
All right, skid marks. For this problem, wait, that's a distance, isn't it? That's how long it took it to stop?
Yeah, 160 feet before coming to a stop. So yeah. And then the question is, how fast was the car traveling when the brakes were first applied?
So velocity, that's what we want to know. What is the velocity when the brakes were first applied?
The derivative all the way down to 50. How long it took that 40 feet per second equal 160.
Okay,
And then plug the time back in.
that sounds pretty good. So deceleration, when we have deceleration, what is that
It's a
normally?
negative.
It's a negative, right? And it's
Acceleration.
the second derivative. So we've seen this.
Yeah.
So now we could possibly start here, right? And do antiderivatives to work our way back.
I couldn't figure out what the constant was though.
Well, the constant deceleration means that the acceleration or deceleration, they're the same. So deceleration means it's negative, right? So if it's 40, you're decelerating, just like gravity is a constant deceleration. When you throw something up into the air, gravity causes it to lose its velocity, right? So it's decelerating that object at a constant force of negative 32 feet
Whatever
per
it
second
is,
per
yeah.
second.
Okay.
So that's a constant deceleration.
Okay.
So this is a constant deceleration. So tell me what you said again. I like that. That was kind of a quick and easy approach.
Take that derivative of 40 all the way back to distance.
Okay, antiderivative, right?
Antiderivative.
So we've got acceleration
Did you replace your exam with
at negative 40. So if that's true, what's the velocity?
Negative 40,
Negative 40t plus a possible constant.
That's the one I couldn't find.
And then
Understand.
what? You want to keep going?
Yes.
stupid?
So if that's the velocity, even though we don't know C1, C1 is a number. It might be 0, but let's allow for the fact that it might not be 0. Let's anti-differentiate this again. Here we go. We were at acceleration. We're trying to work our way back to distance, height, or position. It's a distance in this problem. What do we get here?
Negative 20c squared, or 20t squared plus cx,
C1t
or t.
plus the possibility of another constant, right?
Yes.
And then what are you saying to do with that?
Set that equal to 160 feet.
Okay, the distance to stop. So we do have a distance.
Yeah, I should have known to do that.
Now, what'd you do with the constants?
I can't remember now, but I remember that's the method I used.
Anybody real quick? Because we got about 30 seconds and we have to stop. Any idea?
Put 0
from,
in for the time.
No.
okay,
For the time, maybe.
so think about time 0 in this problem. You want time 0 to be when the brakes were first applied, right?
Right.
When the brakes were first applied, we don't know the velocity, right? So could C1 be this velocity at time 0?
Original, yeah.
Is that true?
Time. Yes.
How far at time 0, so let's call this initial velocity. This represents its initial position. How far, what is the length of the skid mark at time 0 when you first apply the brakes?
0.
Apparently set it to 0.
It's 0, right? You haven't created any skid marks yet because you just pushed on the brake. So C2 is 0. So there's your equation.
Oh. It's easier than I thought.
Okay, and if we need to talk more about that, we can talk more about that tomorrow. See you tomorrow.